My name is Bill Buchanan, and I host a podcast on the world leaders in cryptography. And today I have a true world leader, Victor S. Miller. Hi, Victor.
Hi, Bill. Nice to meet you.
Yeah. And the S for your middle
Yes,
name?
is Saul. I
Oh,
was named that was named after one of my grandmother's cousins.
all right. Okay. And I suppose from an academic point of view, once you've published a paper with the S, then you've got to keep with it.
Yes, well, I found there are a number of other Victor Millers around, so it's always helpful to distinguish.
Yeah, that's right. So Victor is a senior research scientist at Nexus Laboratories. He received his PhD in mathematics from Harvard University in 1975 and was an assistant professor at the University of Massachusetts, Boston from 1973 to 1978. Victor has since worked for the IBM Research Center, the Institute for Defence Analyses in Princeton, Meta Platforms, and SRI International. For his research, Victor has focused on areas of computational number theory, data compression, and cryptography. Along with Neal Koblitz, he was the co-creator of the elliptic curve cryptography method, the inventor of Miller's algorithm, and the co-inventor of the LZW data compression method. For the LZW invention, he was awarded the IEEE Millennium Medal. And for his work on elliptic curve cryptography, he was awarded the RSA Award for Excellence in Mathematics, the Levchin Prize, and the Eduard Rhein Foundation Technology Award. I hope I've got that correct, nearly.
Close enough.
Yeah. Along with being a member of the Information System Security Association Hall of Fame. So, what's your current role and what does a typical day involve for you?
Okay. Well, as you say, my current role is a research scientist. Nexus Laboratories is a small startup which is working in areas well related to blockchain. In particular, their area is what's called a zero knowledge or distributed zero knowledge virtual machine. So, as part of this small research staff, we both have to keep up with what the current improvements are in zero knowledge proofs, which are coming fast and furious, and also interact with our engineering team who are actually building this, and we actually have a functioning distributed zero knowledge virtual machine. Um, it would take a long time to get into all the details, but basically, zero knowledge refers to a bunch of cryptographic protocols which accomplish something which at first sight sounds impossible. It allows you to make a computation. Well, there are two aspects of zero knowledge. The first part, if it's really zero knowledge, it allows you to make a computation with using your own secret information and to be able to convince someone else, with extremely high probability that you actually possess that secret information without actually revealing it. And it turns out such things are really of essential use in a lot in blockchain, but basically there's people are coming up with new ideas about ways that it can be used. It's an old idea that was first, I don't remember exactly how long ago it was first mentioned. I think probably on the
Shafi?
order of 35 or
Shafi,
40 years ago.
Shafi Goldwasser,
Yes,
perhaps?
yes, yes. Shafi Goldwasser and some of her colleagues.
Hmm.
But basically, it was just sort of a theoretical, thought experiment. Wouldn't it be interesting if we could do this? And they came up with sort of general ways of, if you use various things in cryptography, you could do it. But until maybe 10 years ago or so, it was not considered anywhere as possibility of practical, that it would just be far too inefficient. And actually, this sort of parallels. There are two other closely related kinds of cryptographic things called multi-party computation and fully homomorphic encryption. And they actually share a whole bunch of commonality in their ideas. They're not exactly the same, but they have a lot of in common. And they also ran a course like that, where they were proposed theoretically, and it was only in the last maybe 10 years or so, give or take a few years, that they actually started approaching practicality. Quite honestly, I think in order to have very wide use, they still need to improve a fair amount in their efficiency, but people are working very closely. For example, when Nexus, before I joined, they're as a company, as a startup, they're only around 2 years old, give or take a few months. And the first version of their software worked, but it was probably too slow. And the current version is probably, at least 3 or 4 orders of magnitude faster, and more efficient. And we hope to even make it faster. So part of our job as a researcher is to both look at the protocols to see if we can get more efficient protocols, and also look at the nuts and bolts, the underlying low-level thing. So that sort of goes with the kind of thing that really appeals to me a lot, is being able to sort of get very better algorithms for optimizing certain things. And later on, when I talk about my history, I will sort of expand on that a little.
Yeah, yeah, because under the hood there is pairing-based cryptography, and
Right.
you were one
Yes.
of the
Right.
inventors of one of the methods. So we'll come back on to that a little bit later.
Right. Yeah.
So if we go right back to your school days, your early
Ah.
days at school, what were you like as a pupil? What subjects did you like?
Okay. Well, I can briefly go back. So my father was a mathematics major in school,
Ah,
but for various
excellent.
reasons, he didn't really work in that until 1956, when he joined the RAND Corporation to be trained as this new field of computer programmer. And they worked on what was then the world's biggest computer, what was called, it was the Sage. It had a very weird name, the ANFSQ7, which you can look at, but it was an immense, very expensive, huge computer. 6 years later, I started attending the Columbia Science Honors Program while I was in high school. And that's where I actually took my only course in computer programming. I later started Columbia University. Now, that was the one thing. So my father, starting when I was 8 years old, I started reading my father's college mathematics textbooks. And so I pretty much taught myself, everything through calculus and algebra and various things like that. So when I got to Columbia, I was going to start taking advanced math courses. And one of my great mentors was a mathematician known as Serge Lang. I don't know if you know the
Yeah.
name. Serge was quite an interesting character, but he was teaching a course which I would call prospective freshman and sophomore mathematics for prospective PhDs. And so he insisted on interviewing people, and he was very convinced that I knew a lot of advanced math. And basically, in that first year, we went through what would be practically a whole undergraduate math major curriculum. And when I look back, I found out that my first exposure to elliptic curves actually came there without mentioning them,
Wow.
because
Wow.
he gave an exercise which actually, it turned out, proved later very crucial in my analysis of elliptic curve cryptography. But I didn't know that then. Um, and so I went through there, and there were two other professors there who had, a great influence on me, Lipman Bears and Patrick Gallagher. But if you ask what I was like, so I was mostly concentrated in mathematics. However, my sort of hobby when I was there was I was a member of the college radio station.
Oh,
Um,
wow. Yeah.
and I did announcing, but I also, the most of what I did is I worked as a radio engineer for the sports department. So I went on all the sports games, and I arranged, all of the wiring and whatnot. And I that would go too far, but I could tell you really amazing stories about some of those experiences. And then basically, because of Serge Lang was, anyone who knew him was sort of like an unstoppable force. It was impossible to argue with him. So when I went to Harvard, my entering class in the Harvard math department was only 12 students, and of the 12, four were from Serge's students at Columbia. And basically, I was told that he just wrote in recommendation letters, which were one sentence. He said, "You must take him." Yes, and they didn't want to argue with Serge. So Harvard was also an amazing experience. I learned so many things from so many different people. So the very first semester I was there, I got to take a course from the famous mathematician Oscar Zariski, who was one of the pioneers in algebraic geometry. Now, what was interesting is that really also influenced me a great deal in my work on elliptic curves later, because he made a lot of things extremely concrete. And then one of his grad students, Robin Hartshorn, taught the second semester, and he gave a more abstract, and general view of things, which is helpful in thinking, but both the concrete and the abstract are there. And I also was influenced by Raoul Bott, Andy Gleason. I mean, there were a whole bunch, and of course my advisor, but one of the people who influenced me the most so I was in graduate school for 2 years, and I got tired of being a poor graduate student, which I think anyone who's been in graduate school can sympathize with that. And I had been working over at summer jobs doing computer programming, and my boss at IBM, where I was working across on the MIT campus, wanted me to go work for them, and it would allow me to feel a little less poor. And I felt that I could do that and then perhaps work on my thesis research at the same time. It turned out I then went to work for a place called BB&N, which was one of the pioneers in starting the internet.
Yeah, yeah.
And after I was there for about a year, I really came to the conclusion that I really needed to go back to graduate school full time in order to do that. But then I spent the summer at the MIT Artificial Intelligence Labs that summer. That summer was actually a very crucial summer because in addition to doing that, John Tate taught a seminar, I think 2 days a week during the summer on elliptic curves. And I still have my notes over 50 years later, which are invaluable, which is what's really taught me the details about, the ins and outs of elliptic curves. And he had a number of, so for example, two of the other people there were Barry Mazur, who later became an advisor, and John Coates, who was the advisor later of Andrew Wiles. They went through, essentially, in those days, elliptic curves were a really niche area. When I think back, there were probably no more than maybe 20 people in the world who worked at anything at all advanced about elliptic curves. Yeah. And Harvard, it turns out, because of the few people there, was one of the centers of them. That year, they had visitors from Brian Birch and Peter Swinnerton Dyer, who made the famous Birch-Swinnerton-Dyer conjecture. And Brian and I really bonded. So we used to talk every day for a few hours. And Brian was very down to earth in computation, and he influenced me a great deal. But in some ways, I feel like even though he was never technically my advisor, that in a lot of ways he had certainly equal play for that. And so that year, my thesis work was on elliptic curves and modular forms and what are called p-adic L series. These are all of a piece, but it's very technical, so I can't even get into that. But one of the things that was different about me at the Harvard Math Department is at the time I was the only graduate student there who had any experience or skill in working with computers. And later on, they had another graduate student named Joe Bueller, whom I got to know very well and then later worked with, who also did that. But of course, these days it's sort of changed. Now, number theorists, if you look at the history, they've always been big on computation because number theory is very attractive. It can be very deceptive because it's very easy to get a wrong idea about small computation. So you really have to be clever about computation. And so, uh, so I actually both worked while I was there. I was still working as a consultant at BB&N, and then that job at UMass Boston literally fell into my lap because they wanted someone who they felt was a regular mathematician who could start up their concentration in computer science. So that's what I did my 5 years I was there, besides teaching regular mathematics courses. So I started their whole computer science concentration, which after I left split off to a separate department.
Yeah. And for an elliptic curve, you have something like y squared is equal to x cubed plus ax plus b. Was there
Right.
a thing for the mod p at the end, or was it just the analog form of the elliptic curves people were working
Well,
on?
yes, well, you had to work on both. So it turns out that, in fact, bringing up Birch, Swinert, and Dyer, that's what they did. So the original research in elliptic curves that was motivated by Diophantine equations, which is the problem of solving equations in integers. But
Yeah.
it turns out that very early people found that their solutions in finite fields told you a lot about what the solutions in integers were like. And in fact, what Birch and Swinert and Dyer did in their computation is that they actually related, they actually took an elliptic curve over the integers, reduced it modulo a bunch of primes, found out how many solutions they had, and they were able to relate that to a quantity called the rank of the elliptic curve over the of the integers. And this is actually one of their work, and led to the Birch, Swinert, and Dyer conjecture, which is still one of the $1 million Millennium prizes from the Clay Mathematics Institute. So there was always this interplay between finite fields and integers. Uh,
Yeah.
and in fact, that was crucial in what I did later in the analysis of ECC.
Yeah. So go ahead and explain your thought process. How did you come about inventing this amazing technology?
Okay, well, there's a quote that I like. I may be mangling it because it was originally in French from Louis Pasteur. Said, "Fortune favors the prepared mind." And I was well placed to do this. So without getting into things, so one of the people that I became friendly with at Harvard, and later we were close colleagues at IBM, and then later at IDA, was Don Coppersmith.
Yeah.
And Don is an amazing mathematician, is grazing in cryptanalysis and solving problems. So Don made a huge splash back. So Don and I went to a talk, which was probably like in 1982 or 83. There was a mathematician named Fujihara who had been visiting from Waterloo, and he was working with a group of Scott Van Stone and Ron Mullins and so on the Diffie-Hellman crypto system. And they came up with a greatly improved algorithm for actually trying to break what was the standard Diffie-Hellman crypto system over finite fields that are more of use in coding theory. That these were the original Diffie-Hellman system uh, was in the integers mod p, but these were finite fields of characteristic 2, which are very common in coding theory. And what happened is Don was very piqued by this talk, and he and I used to talk a lot about this. And within a few months, he came up with this amazing idea, which just completely broke this system. So originally, system was going to be used by the Federal Reserve Bank of California, and Hewlett Packard and actually Scott Van Stone's company were manufacturing chips to speed up the computation. And Don basically came up, with the help of visiting James Davenport, came up with an algorithm which was programmed out, which after a pre-computation of only a few minutes was able to break individual cases in only 8 seconds. And so at that point, it completely ruined that system. But it got me to thinking. I said, the Diffie-Hellman idea is a beautiful idea, but it seemed to at least have a bad flaw in that it could be attacked in this way. So I started to think about this. And later on in my work in data compression, I was invited to Bell Labs to give a talk about data compression. And I saw two of my colleagues, Andrew Odlyzko and Jeff Ligarius. And while I was in their office, I saw sitting on top of Jeff's desk a paper by René Schoof, which was a fast algorithm for counting the number of points on elliptic curves over finite fields.
Yeah.
And
Order.
I immediately, I asked Jeff for a copy of the paper, and this was actually rejected from the Fox conference. Jeff was very upset about this. But because of my background in elliptic curves, I read the paper. I immediately understood the intricacies of what he did, and I started thinking about, well, maybe I could do something with elliptic curves. In the meantime, his advisor, Hendrik Lenstra, had come up with another way of using elliptic curves to factor numbers,
Yeah.
which had slightly different properties than the other methods. So this sort of got me thinking about maybe I could use elliptic curves in this. And I started to think, so when cryptography is a funny field, because basically it's this competition between people who propose problems that they hope or claim are hard to solve and people who like to say, no, you're wrong. I can break this. So, but basically, so there's the people who propose them and the people who try to break them, and you have to sort of be both. Because in order to propose a hard problem, you have to think, how can I break this? So I knew that in factorization and in discrete logs, there were two methods. There was one called the generic method, which would work over anything called a black box group, where basically you could compose two things, but the actual representation didn't really mean anything. And there was others where when in the ordinary Diffie-Hellman problem, it does mean something because it comes from an integer, modulo p. And the good attacks happened because they were called lifting them to the integers and using something in the integers to decompose them and then pushing them back down again. So that was the only other alternative that worked and worked better. So I said, how would that possibly work? And so I said, here's the analogy for elliptic curves. And I then knew, because of my background, and in fact, going back to the original problem that Serge Lang had me look at when I was a freshman in college, that was actually a crucial thing that had to do with what's called heights of distribution of heights of points. Now, a height is really essentially the number of bits it takes to write down the coordinates as integers,
Yeah.
within a small constant factor, but that doesn't really matter much. And basically, since I knew a lot about elliptic curves, I actually showed that no matter what algorithm you have, it was impossible to get enough points, even if no matter how clever you were, in order to have a good enough chance of making this algorithm work. And that was the analysis that I did in my paper at Crypto 85. And in fact, the crypto conference was new. So Alan Konheim was a mathematician at IBM who was one of the leaders of the group that produced DES, the data encryption standard. And actually, Don Coppersmith,
Yeah.
Introduction to Cryptography, worked on that. Alan then, I knew Alan, but he left IBM in 1980 and he went to become professor at UCSB, and he started the crypto conference in 1981. And so Don told me, he said, oh, well, this is a new conference. He said, I have some result. He said, why don't you submit something? So I did. And of course, the rest is history. And so I also did this maybe somewhat maliciously because I said, I spent a lot of time learning very hard number theory. And these people were using what I felt was actually very simple number theory. So I thought learning hard number theory was good for them. And I said, even if not for them, it actually, and I think this worked, it actually gave work to a lot of, good mathematicians who knew about this. So a lot of mathematicians ended up transitioning into cryptography, who had hard, background in advanced number theory. And I'd like to believe I played a big role in that.
That's right, yeah. And obviously the number of points in an elliptic curve that are possible is known as the order of the curve, because you can obviously have up to the prime number minus 1 points to the power of the prime number, but not all the points are possible. So it's that order is key for the security of the curve.
Yes. So that was another advantage, which I think Neal Koblitz in his paper emphasized, that it was known by Hasse that all the order of the points would fit in a small interval whose radius was around the square root of the prime. And not only that, so Hendrik Lenstra in his paper showed that except for the ends of the interval, that they were actually fairly uniformly distributed. I mean, it's not quite uniform, but it's close to that. And that had the advantage of that Polig and Hellman, Polig was a PhD student of Hellman, showed that in order that there was a vulnerability if the group of points was only divisible by relatively small primes. So you needed a large prime. And it turns out that the original thing, if in the original Diffie-Hellman, their group was restricted to the order prime minus one. So the prime minus one had to have a large prime factor, which made it hard to find this. But basically with elliptic curves, you could choose any prime you wanted, and you'd almost be guaranteed that you could find some elliptic curve which was divisible by a large prime, whose order was divisible by a large prime. So that had an advantage there too.
Yeah. So could you quickly outline how elliptic curve cryptography actually works?
Well, elliptic curve, on the abstract sense, the Diffie-Hellman crypto system could be thought of as a way of just disguising the very simple group of the integers modulo n for some integer n. And basically in the Diffie-Hellman system is that exponentiating really just disguises this group. So you can think of it as a black box group. So black box group are things where you have a bunch of bit strings and you have some oracle which tells you how to add them. And it also tells you when they're equal. Okay, so that's it. And so and elliptic curves are algebraic groups. So that was one of the reasons I did this. So I said, if we're going to do something like the Diffie-Hellman system, in order to be practical, the actual exponentiation and composition in the group have to be fast. Otherwise, people couldn't possibly use them. So I knew that there was a whole series of things called algebraic groups, which basically says that the composition law is just you can get by just evaluating a small number of polynomials. And so there's a whole classification of algebraic groups, which is due to Claude Chevalley, who basically said there are two kinds and they're composed of two pieces. And because of Polig and Hellman's argument, it turns out if you want to cryptanalyze them, that you only have to do it in each of the two pieces independently, and then it was easy to put them back together. And so one of the kinds of pieces were matrix groups, but it turns out they're vulnerable to the same sort of attacks that ordinary, discrete logs have. And the other kind of groups are called complete groups. That's a technical term, and elliptic curves are the simplest case of those. So I said, what would happen there? And it turns out they qualitatively are much different. So the way Diffie-Hellman works is that basically you have this black box group, and the way and then when two people, it was proposed as key exchange, because this was in traditional cryptography, that was actually one of the most difficult practical matters, is how can you have two communicating parties agree on a common secret which nobody else knows about? In the old days, you actually had to do it by having couriers. And but in the internet, you'd like to do it instantaneously or pretty close to that. And basically, Diffie-Hellman said, if I want to communicate with you, then I choose a random number. Of course, this finesses the problem of how to choose a random number, but I'll leave that alone. Each side chooses a random number. They then disguise this by this one-way function, or hope to be one-way function is a function which is easy to compute but hard to invert. And then they send it to each other. And the one-way function is not just a one-way function, but it's a function where it actually is called a homomorphic, where you can actually do the addition while it's still, encrypted, so to speak, by the one-way function. But it turns out that is, well, we'll discuss it later when it comes to quantum computing, but that's actually its Achilles heel when it comes to quantum computing, because Shor's algorithm shows that if you have commutative things, then that's what his algorithm can attack. But basically, it's actually when abstracted that way, it's actually basically a very simple idea. You have a one-way function which also which takes integers mod n, and that also is homomorphic. That is, that even when you have the encrypted version of these things, you can still get the encrypted version of their sum. And that's all there is to it. So basically, the encrypted version of their sum is what each part can compute, but an eavesdropper can't do that because they can't invert the one-way function.
Yeah. And obviously, this was 1986 that you came up with this. And elliptic curve was really a slow burner. I think Satoshi Nakamoto didn't use it, I can't remember, till about 2005. You're looking at 20 years. So did you have any idea of how powerful, how successful elliptic curves would be at the time?
Well, I hope they would be. I mean, one of the problems was at the beginning, because it was seemed to be much advanced number theory, I think a lot of people were afraid of it because, quite honestly, I mean, you don't want to field something unless you feel like you understand it, sufficiently. But eventually, what happened is that a number of people were educated in this, and they found out that, like a lot of things, that to actually implement it really wasn't that complicated. It was just a matter of being able to evaluate a set of polynomials. You had to do it carefully, but in order to understand why, like a lot of things in cryptography, the cryptanalysts, the engineers don't really have to understand the intricacies of the cryptanalysis. They just have to have faith that it's true. And this was the same thing. Now, money always complicates things. So, Ravesh, Shamir, and Edelman started RSA, and this means a lot of money. And at least in their public statements, they sort of disparage elliptic curves, saying, we don't really understand it. But Ron Rivest, in fact, invited me to, and Shafi Goldwasser invited me to give a talk about elliptic curves there the next year at MIT. And Ron then had me sort of act as an unofficial advisor to one of his PhD students, Bert Kaliski, who actually was the first one to implement Miller's pairing algorithm, which I'll get to later. So he and I corresponded a lot by email. And so Ron fully understood that this was something that probably was important. And eventually I felt very vindicated when he gave me the RSA, well, me and Neal, the RSA Excellence in Mathematics Award for inventing elliptic curve cryptography.
Yeah, that's amazing. And did you know of Neal Koblitz's work at the time?
No, I didn't. I had met Neal because Neal was a senior math major at Harvard when I was a first-year graduate student. So I had met him then. And then he went off to Princeton, where he was actually quite a political radical. I mean, ironically, the place that I later worked for 29 years, IDA, was then on the Princeton campus, and Neal was one of the leaders in protesting against them on campus. So I knew that Neal worked in essentially algebraic and arithmetic geometry, as it's called, but I didn't know that he was thinking about all this. It turned out both of us were corresponding with Eduard Lisko. So while I was forming my ideas in elliptic curve cryptography, I was corresponding with Andrew, who's a very sharp mathematician and computational number theorist. And he told me the day when I finally sent my more fully filled out manuscript, giving all my justifications, he wrote me back and said, "This is actually rather interesting coincidences, because the same day that I received that, I received I think it was a letter, it wasn't an email, from Neal Koblitz when he was in Moscow, essentially proposing the same thing." So elliptic curves were in the air, as he pointed out, basically, because of Hendrik Lenstra and the student René Schoof. And, it was just sort of a matter of time, I think, until they sort of emerged, and we just happened to be both well prepared.
Yeah. So obviously the RSA method was patented, and it was then licensed to the company. And I think you worked for IBM at the time that you created elliptic curve. And so why didn't IBM patent the method and make lots of money?
Well, IBM has had a whole system, at least then, of what are called invention disclosures. And invention disclosure is basically you go to a a committee which meets every once in a while, and you make your proposal, and the committee decides because filing a patent is actually quite expensive. In time, they have to take up the lawyer, they have to take up the time of the researcher to work with the lawyer, and I had spent a lot when I was working in the data compression doing that. And basically, a lot of times IBM just doesn't feel like it's worthwhile. And not only that, it turns out IBM was very invested in DES. And in the
Mm.
past, when I had done things involving cryptography, which actually there was a side thing with the data compression, which actually involved cryptography. If we have time, I can tell a little about that. Um, I felt I had encountered a lot of hostility from the IBM Crypto Competency Center about anything, any cryptography that wasn't DES. So in any case, they basically said, well, this is sort of like an interesting pie in the sky thing. And Don said, oh, here's this crypto conference. And, so I submitted it there. And I felt, and, we can get to software patents later. I mean, I have a very mixed feeling about software patents. Um, IBM, its patents are very important to big companies like IBM, but it's sort of interesting how a lot of companies have gone, including Nexus that I work for, have gone to really open source ideas. They feel
Mhm.
we can just put out our ideas, and it's just that we do them better than anybody else. That's the
Mm.
important thing. But that's a whole other matter.
But it could have made you a billionaire. Obviously, IBM would have had
Well,
to
I
license it.
joked I joked with some of my friends. I said I'm not greedy. I would take a thousandth of a U.S. penny for every use of elliptic curve
Yeah,
cryptography,
and you would be a
and
billionaire
yeah, I'd be a
easily,
billionaire. That's right.
easily, easily. The same with the Diffie-Hellman method.
Yes.
I think Stanford didn't aggressively pursue the patent, which was maybe a little bit unfortunate. So it didn't make Marty Hellman and Whitfield Diffie the money they
Well,
probably deserved.
there's also, I mean, patents, at least in the US, would normally last, I think, 17 years. And if it had
Yeah.
been patented in 1985 when I invented it, it was actually 1984 when I actually came up with the ideas. It would have expired long before it actually would have been used widely. So it probably
That's
wouldn't have made much of a
that's right.
difference. Yeah.
Yeah, yeah. It was only when SSL really came along that you had elliptic
Yeah.
curve Diffie-Hellman, and then obviously ECDSA with blockchain and so on. So you're looking at 20 years. So you're
Right.
right. The patents would have expired. So I looked up the proceedings of Crypto 85, where you
Yes.
published your classic paper, and I
Yeah.
see people like Ron Rivest, Audie Shamir, Tahir El Gamal, George Blakely, Shafi Goldwasser, Don Cooper Smith, David Cham, Whitfield Diffie. Do you think that was the greatest crypto conference of all time? And what was it
Well,
like being in that community?
it was actually really quite amazing. Whether it was the greatest, it certainly, see, by then, if you look at the group photo that I gave you, it was still fairly small. There were probably only a little over 100 people. Because
Mm,
before then, cryptography was pretty much the province of governments.
yeah.
And these were a bunch of academics and maybe a few industrial researchers who had some interest in this. There were certainly, in the names you gave, there were certainly big pioneers in the field. There were a lot of other advancements since then. It was, I watched your interview with Neal Koblitz, and I would sort of echo what he said. It was a really interesting and exciting, these people had a lot of new ideas and were excited with that. I remember at that conference, for example, there had been a lot of thought. There were a brief flurry before this of knapsack-based crypto systems.
That's right. Yeah.
And during one of the
Um,
demonstrations, then
Michael. Yeah.
Len Edelman brought his Apple computer where he had written in BASIC a program which broke the super increasing knapsack, where he was demonstrating this. This was not mentioned in the proceedings, but I remember this very memorably. And uh, there was a rump session, which they still have in crypto, but it was much different because it was so small. The rump sessions talks were 15 minutes long and actually could have technical content. And they were much more freewheeling. So Whit Diffie ran the rum sessions at the time, and he would enforce the time limit because he had a super soaker water pistol, where if you went over your time, you would get squirted. I don't think
Yeah,
they do that these days.
yeah. Oh, that's abuse.
I recommend that to other conferences
Yeah,
to keep people on
yeah,
time.
yeah, yeah. That's true. And I've actually got the photograph
Yes,
of that,
yeah,
and it was quite a shock at the time because I think it was Ralph Merkel and Marty Hellman who had came up
right,
with this method, and it looked like an alternative to the RSA method. And
sure.
then, as you say, Len went and cracked it live, and I think Audie Shamir was
Yes,
involved in the
yes, yeah.
cracking
Adi
too.
Shamir did, and then later, as I said, Andrew Idlisko and Jeff Ligarius actually did it in a much more general way, using their theory of their lattice reduction, which
Yeah,
is a whole other episode in cryptography. Uh,
right. Yeah, it must have been a great time to be involved in the field. Obviously, 1978 was like the RSA paper.
yes,
Audi Shamir was coming up with all these new heuristics and
right,
secret shares
right.
and so on. And it really must have been a wonderful time. And do you feel a bit sad that elliptic curve cryptography is likely to come to an end in the next decade or so?
Yes, I do. I mean, I thought it was on the other hand, I think that even if elliptic curve cryptography in its present form, it may come to an end because of the possible threat of quantum computers, it actually changed the direction of people's thinking. Um, and also, for example, there is a fallout from elliptic curves of what's called isogeny-based crypto system. People are still working on that. It's still not
Yeah.
completely clear what the vulnerabilities are. But as I mentioned, the threat from quantum computing or Shor's algorithm has to do in Shor's algorithm uses in a very essential way the fact that the composition law is commutative. So that's why it hits RSA and it hits elliptic curve cryptography and Diffie-Hellman. But the isogeny based, so isogenies are something that are derived from elliptic curves, and their composition law is inherently not commutative. So at least it's not apparently vulnerable to something like Shor's algorithm. Of course, that's why we do research in this. I mean, so the way I picturesquely describe cryptography is that one Holmes, smart and hardworking, proposes some new hard problem, and then a number of people, other smart people, hit away at it for a while, and after a while they become exhausted. And so after a period of time, they said, well, this is all we can do. I guess this is okay. But
That's
there's almost no basic core problem in cryptography which has an absolute unshakable mathematical proof that it's really hard. It's only based on
right.
certain assumptions.
Yeah. And obviously the isogenies have the advantage of us still using the Diffie-Hellman method, where I
Right,
think most of the lattice methods and are using are using key encapsulation. So you encapsulate the key with the public key
right,
of the recipient and send it
right,
over. And that's like going back to the RSA key exchange that your
right.
elliptic curve method overcame. And it's a shame because the psych method in the NIST competition was cracked, not because of the insecurity of isogenies, but because they chose maybe the wrong parameters for it. So it certainly set us back a long
Yes.
way.
Yeah, and that's there's this war in cryptography between trying to make it more efficient and
Mm.
when you so sometimes so one of the problems that happened in psych is that they added extra information which
Mm.
they sent in the clear in the hopes of making it more efficient. And it turns out that that extra information created a terrible vulnerability, which they didn't understand at the beginning. But, and so it turns out there are other alternate proposals using isogenies which don't send this extra information, which, at least as far as they know, don't have a vulnerability like that. But, it's still very hard to cryptanalyze things. So that's why I think you have to be a little on the conservative side. You have to wait till you really look at these things in depth.
Yeah. And so Kyber was selected. We now know it as the boring name of ML Chem.
Yeah. Right. Yes. Right.
And some people kind of worry about the lattice methods and whether there's real proof. And obviously, we're looking at hybrid methods now. So I think elliptic curves have a good opportunity to work together with these
Yes.
lattice methods.
Yes.
Uh, so do you see key exchange really happening over the next few years through these hybrid methods?
I think so. And also it depends on use cases. So the only reason why elliptic curves might be or RSA might be bad is for long-term cryptography, but there's some possible use cases where I would say the secrecy is only ephemeral. In other words,
Mhm.
where if you only need to keep something secret for, you know, a day,
Yeah.
and then after that it doesn't matter, then in fact, things like elliptic curves and RSA may be perfectly useful for that if they're much more efficient. Because, after if the day is passed and it doesn't matter if it's broken, quantum computers, when and if they're built, are going to be tremendously expensive and tremendously expensive to run. So they're going to have to be very picky about what problems they give to them. Uh,
Yeah. So I did my degree in communication engineering, and really the wonder of the LZW method was amazing, and I think it's used in zip. And if you think of TV compression, data compression, that the core of it is that method. So what were you actually working on at the time when you came up with the idea of
well,
LZW?
Okay, that's actually a funny story because I was actually working. We'll talk about later the 801 group at IBM on their building like what was the world's most advanced compiler, and the hardware side was building the first RISC machine. But one day I was talking to our department secretary, and she was upset because she was running into disk quotas. So I said, "Well, why don't you use data compression?" And one of my friends, whom I had known since high school, Peter Capek, had written something using Huffman compression. And so I got interested. I started, I was familiar with that, but then I was home ill with the flu, and I was sort of being driven crazy. So I started reading papers on compression, and I was sort of interested in that. Now, the inspiration for the first RISC machine was an IBM mathematician known as John Cock. John was interested in everything. He later won the Turing Award for his invention of RISC machines. But John was interested in everything, and he had this uncanny ability to spot interesting results that he thought people should work on and know who should work on them. And John would literally barge into your office waving a paper saying, "You ought to look at this." And John knew that I was interested in data compression, and he had somehow, I have no idea how, gotten a hold of a UNIVAC internal technical report by Lempel, Ziv, and Eastman about the what was now called the Lempel Ziv 78 compressor. And he said, "You ought to look at it." So I started looking at it, and I said, "This is really very simple." I said, "How could this possibly work?" But it was so simple, I programmed it up, and it worked fine. But then I looked at it and saw, there were various what I felt practical problems with it. And so I worked on this a while, and I came up with improvements, but a lot of them were just sort of ugly. And so at that point, I wanted to make it faster, and I knew that in the inner loop, that it had to use a very fast hash thing, not a cryptographic hash, but a hash like with hash searching, in hash tables. And so I knew that Mark Wegman, whom I sort of knew, had worked along with Larry Carter. They had come up with an idea called universal hashing, which it turns out now at the time is actually extremely important in cryptography. But they didn't know it at the time. They proposed it for some other reason. So I went to talk to Mark, figuring, could he recommend a good hash function from his family's, that I could use? That was my motivation. Mark then later told me, Mark is now like a senior vice president at IBM. But he told me later, I was very flattered. He said that the most productive half hour of his whole career happened during his conversation with me. So this is one of the things that I sort of regret not being able to be more into teaching, because you've probably found this too, is when you have to sit down and explain an idea to someone, sometimes it becomes much clearer to you.
Yeah.
And that's what happened with Mark, is I was trying to explain to him what was going on, and within this half an hour, we came up with three improvements to the original Lempel-Ziv algorithm, practical improvements, which would make it better. The first two improvements, it turns out, were almost trivial to implement. It only took me like an extra, like 6 or 7 lines of code in my program, and they immediately improved the compression by, at least like 30 or 40%, on practical things. So I said, wow, that's really amazing. The third one required a much more intricate data structure, which took me a few weeks to get working properly. And so what happened, it turns out I told this to the head of our compiler group, whom I had actually known when I was first working at IBM on the MIT campus. He had later also went to there, Mark Auslander, and I told him about this, and he got very excited about it. And the reason he got excited about it is at the time we had the prototypes of IBM PCs available to us before they were available to the general public, and he wanted to use it at home. But the modems which we had were very slow modems, and it was just incredibly painfully slow to do this. And so he had this idea that if you could use good data compression, and this was adaptive, which was even better, that it would make it practical. So he, in a programming frenzy, went home over the weekend and programmed a whole terminal emulator with an API exit for the compression. And I had to turn my program essentially inside out. I had to make it a coroutine. I plugged it in there, and it worked amazingly well. Now, it turns out that we had test cases of essentially data sent to someone's screens during the day. And I found out that simple-minded compression would compress it maybe 2 or 3 to 1. On the first variant, it compressed it by 12 to 1, wow, which was amazing. When I made the more complicated variant, it compressed it by 35 to 1. I was absolutely flabbergasted. I had absolutely no idea that it could do this. But I mean, later I came up with a number of explanations as to why it was doing what it was doing. And it turned out that had a huge impact inside of IBM. I was told that within a few months that we had 50,000 daily users inside of IBM who were using our program. It was essentially the first, it was the foundation of what's called the home terminal program, is, people doing remote work. They couldn't really do it then, before that. And we ended up getting 3 research division awards and 1 corporate award for this. And it also was very important in IBM. IBM made a lot of use of it internally in their distribution for their operating system OS/2 and storing test data for their chip testing, and I can go on and on. So it was very important to them. And it turned out that later on, I ended up serving on a standards committee for its use in the V.42 BIS standard for International Telecommunication Union standard for modems. For that actually gave me a lot of, so my background in computation gave me a lot of appreciation for the low-level nuts and bolts efficiency that's needed. And even there, modems had extremely great restriction on their memory that they had. So they had to change our algorithm slightly in order to use even less memory, even though I don't think it used that much memory, but it needed less. But basically, that had a big impact. Now, IBM at the time, since you asked about patents, this was patented. IBM normally didn't license their patents for money, for royalties. They used to use them as basically bargaining chips with other big corporations to get cross-licensing agreements. But in this particular case, they were persuaded, they and other patent holders which affected the standard were Univac and British Telecom. They were all persuaded to basically license their patents to modem manufacturers for a very small flat fee. and I thought it wouldn't amount to much, but they felt it was publicity. I was amazed at the time that there were actually, I had no idea, there were actually almost 100 different companies that were manufacturing modems at the time. So the last time I looked, IBM had gotten at least $5 million in royalties from our patent.
Wow. Wow.
Um,
Did you see any of that?
well, I saw it, as I said, in the awards that I got. Um,
Okay.
uh, it was just, a pittance compared to that, but it was nice.
Yeah. Yeah. And could you just outline how LZW actually works and where it's used at the current time?
Okay. The way it works is this is Lepel and Ziv's original idea is that you see a stream of characters, and what it does is it keeps a dictionary of interesting strings. Now, the dictionary turns out it has to be structured in a certain way, which I won't get into the technical details, but what it does at each stage, it actually, the original Lepel-Ziv algorithm at each stage looks at the dictionary, finds the longest string, which is in the dictionary, and then encodes it, sends the code of that by an encoding of its index in the dictionary. And then, this is the key part, is then updates the dictionary, the original, by adding a new character because it looks for the longest string that matches. And so since the longest string, when you add the new character, that's a new string which isn't in the dictionary. And so it adds that string to the dictionary. And then what happens in the original Lepel-Ziv thing is it's kept building up the dictionary and kept building it up. But they, at some point, you can't build it up indefinitely because you run out of storage. So in the original Lepel-Ziv thing, it actually then just resets the dictionary at that point and then starts all over again from a simple dictionary of just strings that are one character long. Well, actually, the original one was just the empty string because it knows the empty string is always there. So the first thing that I did is I saw that if you initialize the dictionary to all one character strings, then that gave you a leg up. And it turns out that there was this very intricate thing, which I won't go into, which allowed you to, so what happens is when you transmit the new string and you have this new extra character you haven't seen, you actually have to transmit that character. And in practice, asymptotically, it doesn't make much of a difference, but in practice, that actually is a very significant fraction of your files. So it turns out Mark and I found a clever way of overlapping things so you never have to transmit that character if you initialize the dictionary with all single characters. The second thing I did, because I had been working on operating systems, I was familiar with what's called the principle of least recently used. So in cache and virtual memory, you have this problem where you have a fast memory where you look at things, and then what happens is you only have a limited amount of storage, so you have to get rid of something. And the least recently used principle tells you a thing which is probably the most reasonable thing to get rid of. And I applied that same principle to the dictionary, and that allowed you to use a very small dictionary, which meant that the number of bits you encoded was also very small. And that made a big difference. The third one was that instead of building up new strings by just adding one character, we actually added two consecutive strings, which built them up exponentially instead of linearly. And so that made another huge difference. Now, it turned out because of data compression, that was how I met Dan Bernstein. So it turns out I met Dan Bernstein when he was then an undergraduate at NYU, and
Wow.
because he was a big fan of my data compression algorithm.
Mhm.
So I figured he was a smart fellow if he liked that. So I invited him up to IBM to visit me and Don Coppersmith, and I found out that he was really interested in number theory, and we just happened to both be interested in data compression.
That's excellent. And you advanced work in pairing-based cryptography with the Miller method. Can you outline how this works and why you didn't publish a paper on it?
Okay, well, basically, it works by by emulating the actual arithmetic that you need to add points on elliptic curves. So what I found was that in the original, so I came up with the Ve pairing because Manuel Blum, the famous computer scientist, was visiting IBM at the time. And when I gave my first talk about elliptic curve cryptography, he said, well, if you say it's better than ordinary Diffie-Hellman, can you make a reduction? So I thought, well, that's a good point. So I looked at how I could do a reduction. And then I realized, I knew about the Ve pairing from my studying, you know, elliptic curves, and that would give a reduction, which in fact went the wrong way, but I'll get into that in a second. But I said, well, how can I do this? Because all the definition of the Ve pairing to actually implement it would essentially take exponential time. So that would be useless for a reduction. So I started thinking more about it. And the key point there, Eric Kaltofen, who was a computer scientist whom I knew because he had been visiting the computer algebra group at IBM where I worked for a year. He gave a very interesting talk about you computing with straight line programs. So that got me to thinking along those lines. And I realized that you could actually compute the values of the Ve pairing very intricately by a straight line program. And so it could do it essentially linearly in the number of bits instead of exponentially. Um, and so I wrote this up, and our group at the time really encouraged people to submit things to the two main computer science conferences, Fox and Stock. And so I admitted it. I submitted it to Stock, and it was rejected, probably because nobody knew anything about elliptic curves. And they said, what's the, I gave some applications to it, related to René Scoff's paper. But so I felt at the time that there was really literally only a handful of people, and I knew them all, who could really be interested in this. And you needed a fair amount of background in order to appreciate it. And I was working on a lot of other things, and I knew maybe to actually make it a paper that was publishable for people that I would have to do a lot of background work, filling in a lot of details. So I just basically circulated it to the handful of people that I thought would be interested in it. Now, Hendrik Lenstra spoke about it briefly at the International Congress of Mathematicians the next year, because it almost partially solved an open problem in René Scoff's paper. But what really got it going is in 1993, when I started working at IDA, one of the people I met, because Andrew Lisko had recommended him, was Dan Bonin, who was then a graduate student at Princeton. And he sought me out because he was told by Andy and Lisko that I was a good person to talk to. And I gave him a copy of the paper. And about, that was 1993 or 1994, about 4 years later, he wrote me, and he was then at Stanford, which he still is now, and he wrote me an email and said, would it be okay if we put a copy of your manuscript on our website? And I said, sure, why not? And I said, well, why? And he told me because Adi Shamir in 1984 at the crypto conference, the year before I was there, had this thought idea of what's called identity-based encryption, but he didn't have any way of actually implementing it. And Dan and Matt Franklin and then Antoine Jou had come up with a way of using the Ve pairing. I guess I don't know how Antoine got a copy of the paper, but somehow it circulated. Probably he may have gotten it from Henri Cohen, who is another computational number theorist I knew that I'd given it to. I don't know that for a fact. But basically, they all came up with an idea of using the Ve pairing as a way of getting a practical implementation of Adi Shamir's idea of identity-based encryption. And that sort of exploded it. So within a few years, there started being annual conferences on pairing-based cryptography.
Yeah, that's interesting. And you worked on the IBM 801 project at the Thomas J. Watson Research Center in the 1980s. What were your memories of working there?
Okay, it was really a great thing. So it was called 801 because that was actually the numerical designation of the building that IBM Research was in. And they had earlier named their 701 computer after the 701 building in Poughkeepsie. So that was sort of their analogy. There were a lot of incredible people. There were probably 4 or 5 of the people who worked on that project later became IBM fellows, and a number of them, including me, became IEEE fellows. There were three people on there who had worked on the original Fortran compiler.
Mm.
Um, and there was
1957, was it?
Yeah, in 1957.
Mm.
There was Greg Chaitin, whom I had actually known in high school at the Columbia Science Honors Program, worked there. And what was incredible about this is from the time I learned about computing, I really was very interested in compilers. And so this was a great opportunity for me because this was like one of the most advanced compiler projects in the world at the time. And at the time, they invented a lot of the fundamental compiler optimization techniques that are now in wide use, in LLVM compilers and things like that. Um, and so it was really, IBM was really great because we had a lot of incredibly smart people who worked together in the same room. We would bounce ideas off each other. John Cock would wander in and he would give us ideas. They were building, what was then one of the world's fastest computers right across the hall from me.
Mhm.
It was, and just people were so enthusiastic, but they knew at IBM Research that people, if you were sharp people, you always had side projects, you always got interested in things, and they always gave you room to work on these things because they figured that they might pan out. So I worked on that project for, let's see, from 1978 through the end of 1983, so about 5 years. And it was really an amazing time. I learned an incredible amount. I also learned an incredible amount about working with people. I mean, I encourage, when Greg was, so I had come up with some suggestions of doing things, which ended up really completely changing some of the way that they generated their intermediate instructions. And Greg Chaitin is one of these amazing people who goes into these programming frenzies. So there had to, I proposed, I said, well, if you change this following thing, this would have this various advantages there. And I said, but it might be complicated. And Greg took it. He stayed up over an entire weekend. I don't think he got any sleep, and he completely implemented the whole thing. I mean, it was just amazing to work with people like that. Uh,
Yeah, and I think in 1986 you wrote a paper called Short Programs for Functions on Curves, but you didn't publish it at the time. Again, this is another
right.
paper that you didn't
Right. That
publish.
was that. Yeah. Yeah. That was the paper which I referred to earlier that I submitted to stock. That was rejected. That I just circulated among a handful of interested people.
Yeah,
Uh,
but why delay the? Because you
Oh,
rewrote it
I
in
don't know. I,
2004.
you know, pe people who know me, they sort of yell at me because they said you're very bad about, perhaps it's, I'm a little too perfectionistic in things.
Yeah.
So what happened once pairing-based cryptography got to be a big thing, the Journal of Cryptology decided to publish a special issue on pairing-based cryptography, and Arjen Lenstra, who was the editor of that special issue, told me, I'd like you to write a lead-off paper for this, expanding on your 1986
Oh.
paper. The 1986 paper was only like 9 pages long because in those days, those conferences had very
Mhm.
strict limits because they were published in pages.
Mhm.
And the paper which I wrote for the Journal of Cryptology was probably like 35 pages because I felt in order to make it accessible to people, I had to expand out a lot of details, and I could not just appeal to very advanced mathematical things. I had to actually work out all the details and give justifications to people with a minimum amount of background. So that actually took a lot of work because I had to sort of distill out some of the advanced things into much more concrete things. Uh,
And your career, I think, shows that you've worked with some amazing people in cryptography. It's almost like an A to Z of
yeah.
the people in cryptography. I know it's very difficult to do this, but whose research work has inspired your work mostly?
Oh, in cryptography, there are different. So a lot of, so I view number theory and cryptography, a lot of things as sort of a piece of work. So, for example, Brian Bircham, I mentioned, really inspired me a lot. I mean, Don Coppersmith was always great to work with. I mean, we only finally, once he was at CCR, at the Institute for Defence Analyses, we actually did write an outside joint paper together. Um, but Don is really great in that he has this very deep understanding. Also, Andy Adlisco and Jeff Ligarius are both, amazing people. There are so many different people. It's sort of hard to single out one. I mean, for example, since I view this all of a piece of algorithms, I mean, Don Knuth, for example, I mean, is, when he first came out with his first Art of Computer Programming, I immediately, and I think it was like 1968 or 67, I immediately bought it and sort of went through it. I know a lot of people in computer science said, there's too much math in here. And I said, no, that's great, But, so I could go on. I mean, there's a
Yeah.
whole list of people I could think of.
Yeah. Yeah. So what's sustained your love of maths, data compression, and cryptography over the years?
Well, I get excited by challenging problems. Uh, and sometimes I've changed. So over the years, I've gotten extremely interested in other things like satisfiability solving, just combinatorial optimization, matroid theory. But they all, because I encountered them, maybe in looking at some other problem, and I said, this is interesting. So I see a challenging problem. I mean, it's a psychological thing. How does it appeal to you? But sometimes, I mean, I'm sure it happens to you too. You'll see
Yeah.
something and it'll just grab you,
Yeah.
and you feel
Yeah.
like, I have to work on this. I have to understand it,
Completely.
and then that's exactly what happens there. And
Yeah.
sometimes it takes you on. So, for example, I think this just as very recently, I was grabbed by there's a group that Richard Chappell runs. Called Math Fun. And somebody just mentioned some particular problem about something, combinatorial problem about something called sum free sets. And so I said, this is interesting. So I started doing computation on this, not even motivated by anything having to do with work. Well, just last week at work, Jens Groth, who's one of our other
Mhm.
researchers, said,
Yeah.
oh, well, there's these things with sum free sets which are of use in calculating expander codes, which is something that we may want to look at. And I said, how strange. I was just looking at that and it had nothing to do with cryptography, and yet there's a direct application. So I've always found that no matter what I get involved with, even if it doesn't appear to bear directly on a problem I'm working on, it always seems to come back, to something. It's quite amazing. I have no explanation.
Yeah. And this is Groth who did the zero knowledge proof
Yes,
work.
yes,
Wow.
yes,
It
yes,
must be a real privilege to work
yes,
with
yes.
people like that.
Yeah. So our research group is just small. We just have four. We have me and Jens and Michel Abdallah and a young, very sharp cryptographer, Arcacciatori.
Mhm.
You may not know the name, but I predict in a few years you will know him.
Yeah.
Uh,
Yeah.
but but it's small, but mighty, I hope, right?
Yeah. I think the small,
Yes.
great cryptography teams are much better than large, faceless corporations
Yes.
often. And so why did you take the route through industry and not through academia? You could have became a
Ah,
professor like Neil.
well,
Why industry?
I actually, in some sense, we have security. I regret not having done that. It was, at the time, um, I had been at UMass Boston for 5 years, and my department loved me because I had basically started up this whole thing. But the university at the time was going through a lot of problems, and the whole job market in academia was just terrible at the end of 1978. And
Mhm.
I had some friends who both worked at Bell Labs and at IBM Yorktown. For example, Stuart Feldman, the inventor of Make and other things, was a friend from
Yeah.
graduate school. But I had some friends at IBM, and they arranged to get me a summer job there at IBM in 1977 at Yorktown Heights, and I really liked it there. And I found out that when I went there, I literally doubled my salary. I felt very sort of poor, because the university had frozen our salaries, they had frozen promotions, they had done all these things, and it was getting very unpleasant. And I found the people at IBM at the time, they were as sharp as any people in academia, and it was a very stimulating place. And I only left IBM because the company was undergoing a big upheaval at the time. And because of my work in elliptic curve cryptography, the people at IDA were eager to recruit me.
Yeah.
Um, and so that's where I went. And that was that place was, you've not heard of most of the people who work there, but they are some of the sharpest people in the world. It was
Mm.
incredibly stimulating working there.
Yeah.
Um, and because since they work in secret for the government, almost all our publications are internal and you never know about them. I know you've spoken to Cliff Cox, whom I know quite well.
Yeah. Yeah.
And it's
He's,
the same thing. I'm sure he let you know about that.
that's right. Yeah. It was only just recently that it was revealed that the three of them created public key encryption,
Right.
public key cryptography. And obviously there's a parallel work with RSA and what Diffie-Hellman. And so we talked about patenting cryptography methods, and you look at the SNOR patent, it was held back for
Right.
decades, and now
Yeah.
we're using it in EDSA
Right.
and X25519 and so on.
Right.
So are they a good thing or a bad thing? What would you advise to any entrepreneur?
Well, it's really hard to know. I mean, the problem is, the patent, so when I went through my patent, I worked with this wonderful patent lawyer at IBM who taught me a lot about patent law and about the motivation for it. The whole motivation of patents is to make sure that people do not keep innovations secret because be and so the idea of patents is that they teach and improve the general technology, and as an exchange, you give someone an exclusive rights to that for a limited period of time. The real problem with a lot of software patents is it's not completely clear, because a patent, in order to be patent, has to be non-obvious. It has to be something that the state of the art wouldn't come up with themselves. And it's very hard to make that distinction. Um, so patents certainly, help companies in the meantime with their cash flow, but it's very frustrating in that will patents actually keep progress at bay? So I'm not alone in this. I think there are a lot of people in computer science who feel very dubious about software patents, or at least the state of them. The question is, how non-obvious should they be? And as I said earlier, a lot of companies have now gone to the model, which took a long time to go, of open source, feeling that, to use a quote, I think from Lyndon Johnson, going, a rising tide lifts all boats. Basically, if you have a new idea, somebody else can come up with a new idea, and it helps everybody. And where companies can make money is because they implement these ideas and give support in a superior fashion. So, this may not be everybody's cup of tea, but I guess that's my own
Yeah.
feeling. Yeah.
I suppose academia is built on that type of research where you're building on the shoulders of giants and it's incremental. Like GPS is a good example. The GPS in your iPhone took 20 or 30 years, and it wasn't one person who created the
Right.
method. It was really built and this compression is a good example too.
Yes.
It was
Yes.
really incremental change that allows us to have streaming video and
Right.
audio, MP3 and MP4
Exactly.
that we have now. And
Exactly.
so, what do you think the next decade looks like in cryptography? You started off talking about zero knowledge proofs. Are they the future? Is homomorphic encryption going to be on the rise? What's it looking like for the
Well,
next decade?
I think that all three that I mentioned before, there's also what's called private information retrieval. I mean, they're all sort of closely related. They use a lot of similar techniques, but they're not the same. I think, as I said, MPC and FHE and zero knowledge all are getting at the point where they're getting generally practical. there still needs to be a lot of, underlying efficiency to really allow them to be more widespread. I mean, this actually happened with elliptic curves in some ways, because, the original proposal that I gave, since I felt it had to be concrete, you know, gave a certain, say, here's a way of doing it, and you need for each addition, you need 26 multiplications, so on. And now people like Dan Bernstein have gotten it down to only, much smaller, and it will be the same thing there. And I think as things become more practical, you'll find more interesting uses for them. Um, and, so it's sort of hard to say. Of course, with the widespread small devices, there's applications in Internet of Things. There's applications, in drones. I mean, it's only limited by your imagination. But I think, inherently people feel that, so for example, I did, while I was at SRI, I did some work for a low Earth orbiter satellite company that was using a different kind of encryption in order to preserve, their access to their premium service. So there are all sorts of applications people might have, but they're not going to come into the fore unless things become efficient enough so that they can actually be used. And I think that's going to be a lot of things. Of course, there are going to be people going to research. I mean, as you point out, with lattice-based cryptography, a lot of people are still going to be working on cryptanalysis of that. Are there flaws in there's general lattice-based cryptography or in the particular implementation that we're using? You know, every little work makes us a little more sure about it. So I'm sure that, so that's the part of academic cryptography. And as I said, before the academic cryptography, when it was only the province of governments for the most part, there wasn't all that much work on complicated cryptographic protocols because there was a very relatively limited use of cryptography. But after it became, an outside thing, people, more and more of the crypto conference are related to what I call cryptography, uses of underlying, so there are core problems in cryptography like ECC, and there are the protocols that make use of them. And there's more and more work on those because those are the things that you actually need to feel them. And so I think there's more work on that. There's also more work on provable cryptography. I think this is going to be absolutely essential because right now, all of these proof systems like Lean and HOL and ROC and things like that allow you to make up mathematical proofs. Because I know when you spoke to Neal Koblitz, he pointed out that his work with Alfred Menezes was essentially making criticisms of provable cryptography because these people gave informal proofs. But now when you can actually formalize these things, you can actually, find, little holes, little side cases which you haven't treated. And those are often what an adversary can exploit. And so you don't want those. So in fact, that's going to be, I think, a big trend in cryptography is that all these protocols are going to have to be proved. And I know that, for example, TLS, in the new version of TLS, that was developed along with the proof of that. And they actually found some holes in their protocol in the process. So I think that's going to be what's going to happen in a large part in the future. But that's just my opinion.
That's great.
Yeah.
Yeah. And if you could change one thing about your career, you have had an amazing career and invented so many great things.
Yeah.
What would it have been?
Well, I actually would have liked to have gotten back into academia because I actually enjoy lecturing and teaching. And as I pointed out, one of the, a lot of academics, I mean, I'm sure is sometimes teaching can be a bit of drudgery, but on the other hand, as I pointed out earlier, is sometimes when you're forced to actually explain something, it becomes clearer to you too. And that's always an exciting thing. And of course, talking with, young people have, us older people, have the wisdom of the years, but the younger people have a lot more energy than we do. Well, I don't know. I speak for myself. I don't know about you, but in their energy, even though they may not have enough background, they can, in
Yeah.
fearlessness, they can actually stimulate you a lot more.
Yeah.
Uh,
Yeah, and I think you are, and you would have been a great teacher. So thank you so much for
Welcome.
inventing elliptic curve cryptography. I've spent so long researching the topic, and it took almost years before I really got it. And
I
once I
understand.
got it, then it was wonderful, and I still love elliptic curves and using elliptic curve cryptography. So thanks so much for using
Great.
up so much of
Welcome.
your time.
Sure.
Hopefully, if you're in the UK sometime, you can visit the city of
Sure.
Edinburgh and give us another talk. So thank you so
Okay.
much.
All right. You're welcome. All right. Good to
Thank
see you,
you.
Bill.